Hello and welcome back to this course on computer organization. So in the last couple of weeks, we looked at, the move instructions, we looked at the ALU operations. So what we are going to do now is to go into some more interesting instructions that will allow us specifically to do what is known as branching and looping. Okay, so the idea is, when you do an if condition and you want to, fork the program into two different paths, then in the microprocessor, it will effectively to translate to some specific instruction like this. Okay, so the basic idea is that we want to transfer control to another location, right? We want to transfer, I'll say not transfer control, execution. Okay, so let's assume that we have some random program like this EAX, 0x34, move EBX, 0x26, and then I do add, and let's say EAX, EBX. Okay, so like I told you last week, this will translate to some sort of machine code, and that machine code sits in memory, and the program executes exactly in this order step. It executes exactly the order that's written here: instruction 1, 2 and 3. Okay, the instruction is fetched from the memory, the instruction pointer then points to the next instruction, you fetch that from memory, then you decode, you execute, you again, the instruction pointer now again points to the third instruction, which is the add, you fetch that, you decode, you execute, and so on. Okay, so now let us assume that after doing this, I want to just transfer my execution to some other point. Okay, so normally the program would have simply continued like this in memory to the fourth instruction, okay, as shown here. Now, this instruction could now be something like this: JMP to some other location. Okay, I'll tell you what this word location is here. This is just a label, okay, but in reality, this will translate to an address. So, for example, let us assume that I am going to, in location 0, somewhere in memory, I am going to say this is what I am going to put here. Okay, so let me do X or EAX, EAX. So what is this going to do? And I am going to say this is what I call location. So this word location actually is a label that is going to correspond to some point that we have written in the code, but when this actually translates to a real program, it will get translated to an address. Remember that this instruction itself is going to sit in some part of the code memory and has a certain address. The instruction pointer is going to be made to point to that. So let's assume that in this case, initially we made the instruction pointer point to this. Okay, EIP was made to point to this particular location. So let's assume that is 0x, C100. Yeah, okay, and or let me call this 04. Okay, so my EIP instruction pointer, I am going to assume that I have loaded it with 0x C100 004. Okay, and I said start executing the program from this particular point. Okay. So what you would now do is you would bring the move EAX, 0x34. So EAX will get 0x34. EBX will then get 0x26. Then you add EAX and EBX and the result gets stored. So here at this point, effectively EAX will get 0x34 plus 0x26. So this will be what? 5a, 0x5a, right? 0x5a. This is exactly what the result will be in EAX after the execution of this. Now I come to the fourth instruction, right? So the C108, right? 0x C1000008 is this, and so on, right? Every 4 bytes, I am assuming that each instruction is occupying 4 bytes. Okay, this may not be true in x86, but I'm just, for the sake of simplicity, I'm assuming everything just occupies 4 bytes here, right? So at this point, when you have executed instruction 3, right, your EIP will be pointing to this particular instruction. Now what is that? That is simply saying jump to the location. What is the location? This location address, now if I look at it, it would be 0x C1000000. This is what I am calling location, right? So when we write a program, we do not know in which part of the code memory this is going to go and sit, right? Therefore, we have to use this label, and which is also English readable, understandable by the human easily, to represent that address through some alias, and that's exactly what we are doing here. Location is just an alias for the address. When the program gets loaded into the code memory, this will translate into a number, a hexadecimal number, which actually represents that address, right? So now when I come to this, the fourth instruction here, it says jump to location, and therefore this instruction is effectively going to load EIP with the address of this location, whatever that location is. So it will load it as 0xC1000000. Okay. Now when you do this, the instruction pointer, normally when the instruction at location 4 was being executed, right, the fourth instruction, not location 4, fourth instruction was being executed, the instruction pointer would have actually pointed to this place to actually fetch the next instruction. But now you are telling the processor to replace that value with whatever instruction has been provided along with the jump. Okay, and therefore this EIP will get loaded like this, to this value, and the control of execution will go back now to this particular point. Okay, now once you do that, you are going into the C1, all zeros there, you do XOR EAX, EAX, that means you have cleared the EAX register. Then you come to the instruction, the first instruction, where you are trying to load EAX with 0x34. Again you go to load EBX with 0x26, do the addition, and the result will be in EAX register. Again you are jumping back. So if you look at this particular piece of code, right, in the microprocessor, suppose you pointed the EIP to this location and said execute, or for that matter you pointed it anywhere in this place and said execute, this would just go into an infinite loop of executing the same piece of code again and again. Okay, but the focus out here is to tell you that I can transfer the control of execution to an arbitrary point in the code using this jump instruction. Now in the earlier case, it was an unconditional jump, okay? But many a time, if you remember in C and in C programs, you would use for I equal to 0, I less than 10, or if I less than or equal to 10, you would have some condition, right? And therefore, you would have the idea of conditional jumps, where I want the jump to happen only if some condition is met. Otherwise, you just continue as if there is nothing that's, that is changing the path of the execution there. Okay. So, for example, let me give you this particular example here. Let us say that depending on what is in EDX register, I will either add or I will subtract. Okay. So, let us look at that. So, let us look at this case. I have EDX. Okay. If EDX register happen to have the code 0x38, okay, then I need to do addition of two numbers that is going to be in EAX and EBX. If the code is 0x39, then I need to do subtraction. Okay. So, depending on what is in EDX, I am now going to alter my operation that needs to be done on these two registers. Okay. So, let us look at that. EDX equal to this. So, I am going to start with the same code, move EAX, with some arbitrary value. Okay. This is, I am going to choose immediate data. It could be any random value that I am initializing, 0x85, and I will say move EBX with 0x49. Okay. Now, EDX value could get set through some other code, and before I come to this point in the code, right. So, somewhere here there is something that will set my EDX value. I do not know what that value is, right. However, I need to check if it is 0x38, then I need to do something. If it is 0x39, then I need to do something, and so on, right. So, what I can do now is I can use the compare instruction, the CMP instruction, which is going to compare EDX with 0x38. So, what am I doing here? Effectively, the compare instruction is going to do the following. Okay, or I will not even do compare, I will do the subtraction. For now, I will not even introduce a new instruction called compare. I will tell you what CMP does later. I will do subtract EDX comma 0x38, right. So, what is going to happen here? I am going to take the value of EDX. EDX will get replaced by EDX minus 0x38. So, let us say that EDX itself had the value 0x38. Okay, what I wanted to do was addition, and therefore EDX itself was loaded with that particular value. Then you subtract this. The result eventually EDX after this operation, okay, if EDX was equal to 0x38, implies EDX will be 0 after this, right. So, now what I can do, I will subtract this EDX 0x38, right, and then say, I will say jump on 0 to some other part of the code where I am going to do addition between EAX and EBX. Okay. So, I will say jump on 0 to location addition. Okay, addition is a label, we are going to correspond to some address in memory. I will come to what that piece of code is later. So, therefore, the execution flow is going to be as follows. It will be like this. When you come to jump on 0, what it is going to do is, this subtract operation that we did, EDX minus 038, whatever any ALU operation that you do will go and set what is known as a flag register. Okay, so let's come back to that. So any ALU operation will set a flag register. Now, what are these flag registers? It's basically again a flip-flop, a bit that is going to represent a certain state. So, for example, the flags that are present in x86, some of the flags are carry, then 0. You know, two important flags are these, carry, 0, then there is an overflow. You know, there are many other flags which I am not going to get into in this particular course because they are not so relevant, because this is not an x86 microprocessor course. We just want to understand the basic functionality. So we will just stick and restrict ourselves to the discussion on the 0 flag. So 0 flag is when you do an ALU operation, if the result of that ALU operation happens to be 0, then the 0 flag will be set. Okay, set if ALU result equal to 0. Okay, now very important to note that if I move some data, right? So for example, if I do move EAX, 0x 0000 whatever, right? If I do this, the result in EAX is going to be 0, but this will not go and set any flag in the flag register because this is not an ALU operation, it's just a move operation. This is how it is in x86. Okay, so anyway, so the 0 flag can be set and will be set after every ALU operation, right? So when you do, in this case, when you do subtract EDX, 0x38, it is going to perform the subtraction, and if EDX had 0x38, you subtract, you get 0, the 0 flag will get set. So the jump on 0 addition here is actually saying don't unconditionally jump to this addition label, but instead you jump only if the 0 flag is set, right? So that's what we are trying to say here. If it is 0, if EDX had the code 0x38, then you do addition of the two registers. If the code was 0x39, then you do subtraction, right? So therefore, somewhere here, right, I'll write that there is a label corresponding to an address which is going to do addition of the two numbers for me. So what will this piece of code do? Add EAX, EBX. Okay. So I'll complete this piece of code a little later. Okay, remember this is not complete. I've not even told you how the flow will come here, then go back. You know, there are a lot of problems, right? Because when you come to this instruction, right, and let's say the 0 flag was set, then automatically the program execution will jump from here to here. Okay, now when you go there, how do you then come back? Because normally I would have wanted this piece of, the execution flow to continue out here and then finish off something else, right? So I also have to tell you how to come back to this place, right? Now, after this, if the 0 flag was not set at this step, that means the code was not 0x38, right? Then I am going to again check subtract EDX, 0x39. Okay, now there is a problem because EDX was supposed to store the code or the operation that I wanted to perform on these two registers, EAX and EBX. But by doing subtraction in this step here, I have lost that code. EDX value is gone, right? And that is precisely why we use another instruction instead of subtraction called compare. Compare effectively does a subtraction operation in the ALU but will not go and alter the destination register. Okay, so again let's take a small detour. I have two instructions, subtract EAX comma EBX. It will do EAX will get replaced by EAX minus EBX and appropriate flags will be set. Right? So if the answer is 0, then it will do something, it will set the 0 flag. If there's an overflow, it will do that. If there's a underflow, it may set various flags in the process. On the other hand, the compare instruction EAX comma EBX does something very simple. It will do EAX minus EBX, but it will not write the result back into EAX. This will not happen. Okay, and therefore it only does EAX minus EBX operation in the ALU, and then the same flags will be set. Exactly same flags that were set by the subtraction operation will be set even by the compare operation, right? Therefore, the compare operation is ideally suited for such cases where I don't want to erase my EDX, which is supposed to store that code, right? It's the sacrosanct code that is in that register. I shouldn't be erasing that. So therefore, you do compare. So here also, if the 0 flag is not set in this step, that means that the operation is not addition. I need to check if it is subtraction. So then I will do compare. Okay? And then I will do jump on 0 to subtraction. Okay? Now what is this subtraction code? I am going to now copy this piece of code into another page so that I get more space there. Right? So I am going to now introduce another thing called subtraction, right? So what am I going to do here? I am going to if subtract EAX comma EBX. So here I am saying EAX will get the value EAX plus EBX. Here I am saying EAX will get EAX minus EBX. Right? Now, the key point is that the execution flow has gone in a certain way and I have caused a branching to happen. The program is going to fork out into the addition or the subtraction stream depending on the code that is in EDX register. And therefore, I have to now tell it what to do after you finish this operation, right? So, after you finish this operation, I am going to tell this guy JMP, jump unconditionally to finish. What is finish? FINISH. This is the last line, right? And I can do whatever I want at this point, okay? I could, for example, the answer is in EAX register, right? I could move the value of EAX to some address location, or I could maybe the last step, right? I will move the answer to ECX. Move ECX comma EAX. Okay.